Welcome everyone to the topic analog electronics. We have already done two tutorials under this topic, semiconductors and PN junction. The links to those two tutorials are given in the description below. Today we will be looking into a new topic, rectifier. The first question arises that why do we require an rectifier and what is a rectifier? Now, rectification is a process in which a harmonic AC voltage can be converted into a unidirectional voltage, which is also called the DC voltage. This process is called as rectification, and the circuit which can achieve this is called a rectifier. Now, coming to the question, why do we require a rectifier? The current that we receive at our home is alternating in nature. That is, it has a positive going cycle and a negative going cycle. Whereas many devices in our everyday use are DC operated. That is, they have either a positive cycle or a negative cycle. So there is a requirement of an interface which can convert this alternating voltage into its DC equivalent. So we can use a PN junction because in case of a PN junction, as we have seen in the earlier tutorial, it offers negligible resistance when it is forward biased and offers a very large resistance when it is reverse biased. So the current in the forward bias is quite large as compared to the current when it is reverse biased, which is generally neglected, and hence this diode acts as a unidirectional device which conducts current only when forward biased. Now this property of it makes it a very good contender for rectification purposes. Depending upon the number of diodes or the combinations of diodes that we use, we have three different kind of rectifiers: a wave rectifier, full wave rectifier, and full wave bridge rectifier. We will look into the working of the half wave rectifier first. As you can see, the half wave rectifier has an AC source coupled to a transformer, and there is one single diode through which the current can flow, and it goes through a load resistance RL where output voltage V0 is obtained. The use of transformer permits us two advantages. Firstly, it allows us to step up or step down the AC input voltage as per the requirement. Secondly, the transformer isolates the rectifier circuit from the power line and thus reduces the risk of electric shock. Now, when we will apply the AC supply to this diode, it will conduct only when the polarities are such that the diode is in forward bias condition. For the other half cycle, the diode will be reverse biased and it won't conduct any current. Let us see how it works. When the positive going cycle is given, the diode is forward biased for such a cycle and the current flows through the diode D, the load resistance RL, and comes back to the transformer. In the second half cycle, which is the negative going half cycle, the diode D is reverse biased and there is no current through the load resistance RL, and hence there is no output. Let us look into the output waveform of such a half wave rectifier. On the top of the figure is the supply voltage in red, and on the bottom is the output voltage in blue. You can see that when the diode conducts, then only you get an output voltage. The output frequency of this output is same as the input frequency. The negative maximum voltage, that is the peak inverse voltage, should be less than the breakdown voltage during the reverse bias so that the circuit works smoothly. The output, as you can see, is not exactly unidirectional as we have seen in the textbooks of class 9th or 11th. It contains alternating components whose basic frequency is equal to the supply frequency. Therefore, an elaborate filtering is required to produce a steady direct current. As we can also see that the AC supply delivers power only half the time, that is during the forward going cycle. The negative going cycle does not deliver any power, therefore the output is also low. To overcome this, we will look into another design, and that is the full wave rectifier. In case of a full wave rectifier, two identical diodes D1 and D2 are used to obtain the full output during the complete cycle of supply voltage. In this case, the transformer that we use is a center tap transformer, and the load resistance is connected to that center tap. So, in the positive going cycle, diode D1 conducts, D2 doesn't, as it is reverse biased, and the current flows through D1 and load resistance RL, where you get an output voltage V0. In the second cycle, that is the negative going cycle, diode D2 conducts, D1 doesn't, and the current goes through D2 and RL, where again a voltage V0 is obtained. Let us look into the output voltage waveforms of the full wave rectifier. When D1 conducts, you get a positive going output cycle. When D2 conducts, the negative going supply voltage is converted into a positive going output voltage cycle. So for each conduction of the diode D1, we get a positive going cycle across RL, and for each negative going cycle, D2 conducts and we get a positive going cycle again. Hence, the output frequency is twice the input frequency. Once again, the output is not exactly unidirectional. It contains the changing components, which we call as ripples. The DC output in this case is small, as each diode utilizes only one half of the transformer secondary voltage. This full wave rectifier has certain disadvantages. The full wave rectifier requires a center tap transformer, which increases the cost of the circuit, and it is also difficult to locate the center tap on the secondary winding, which is crucial to the proper functioning of the full wave rectifier. The peak inverse voltage is also twice that of a half wave rectifier, and hence there was a requirement to create another rectifier which will overcome the limitations of this particular full wave rectifier model. It was overcome in a model called the full wave bridge rectifier. In this model, we see that there are four diodes which are connected in a bridge formation, and at one point of time, two diodes conduct and the other two don't. We'll look into the conduction right now. In the positive going cycle, the current flows from A to D4 to RL to D2 and to B. The diode D1 and D3 in this case remain reverse biased and no current flows through them. In the negative going cycle, the current flows through B, D3, RL, D1 and A, and in this case diode D4 and D2 remain reverse biased. So there are two cycles. For the positive cycle it is A, D4, RL, D2, B. For the negative cycle it is B, D3, RL, D1, A. Let's look into the output waveform of the full wave bridge rectifier. The positive going half cycle of the supply voltage produces a positive going half cycle of output voltage when the diode D4 and D2 conduct. When the diode D3 and D1 conducts, the negative going half cycle of the supply voltage produces a positive half cycle again. So the output waveform is as same as the full wave rectifier, but it doesn't require the costly center tap transformer. Also, the peak inverse voltage of each diode is half of that of the previous case. Owing to its advantages over the previous two type of rectifiers that we have seen, This is the most commonly used rectifier. Now let's look into certain technical aspects of rectifiers. The first is the rectifier efficiency. It is defined as the ratio of DC power output to the applied input AC power and is denoted by the Greek alphabet eta. Let us try to find the value of this efficiency for half wave rectifier. Now the DC output current for a half wave rectifier IDC is Im by pi, and the AC input current to that circuit is IRMS, which is equal to Im by 2. This Im is the peak current. The DC output power across the load resistance RL is given as IDC square into RL. The AC input power to the circuit is IRMS square into RD plus RL, where RD is the diode resistance. So the rectifier efficiency, according to the formula that we have seen ago, that is DC output power divided by AC input power, we get 0.406 by 1 plus RD by RL. Now, if this diode resistance RD is very less than load resistance RL, then the maximum rectifier efficiency for a half wave rectifier is 40.6%. Let us compare it with the full wave rectifier. For a full wave rectifier and a full wave bridge rectifier, the DC output current is IDC equal to 2 Im by pi. AC input current is IRMS, which is Im by root 2, where Im is the peak current. The DC output power is again IDC square into RL, and the AC input power is IRMS square into RD plus RL. In this case, the rectifier efficiency is 0.812 by 1 plus RD by RL. Again, if we consider the condition that diode resistance is very less than the load resistance, then the maximum rectifier efficiency is 81.2%. So we can see that the rectifier efficiency of a full wave rectifier is quite large as compared to the half wave rectifier. Another factor which we need to consider about a rectifier is the ripple factor. The AC components that are present in the DC output of a rectifier is called ripple. The effectiveness of a rectifier depends upon the magnitude of AC component in the output. The smaller is this component, the more effective is the rectifier. So the rectifier must have as less AC component as possible. The ripple factor R is defined as the ratio of the RMS value of the AC component of the output current to the DC component of the output current, that is IAC by IDC. The RMS value of the total output current is given as root of IAC square plus IDC square. That is, the RMS value of the AC component can be given as root of IRMS square minus IDC square. Hence, a general formula for the ripple factor R is root over IRMS by IDC square minus 1. If we put the value of IRMS and IDC for a half wave rectifier, we get R equals to 1.21, and for a full wave rectifier, R equals to 0.48. So we see that the ripple factor for a full wave rectifier is quite less as compared to a half wave rectifier. Combining it with its rectifier efficiency, the full wave rectification is invariably used whenever there is a requirement for conversion of AC to DC. I hope this topic has been of interest to you, and here we finish the diode and its uses. As we have seen, the output is still not completely DC, so I would request you to go and read about filters, voltage stabilizers, half wave voltage doublers, which actually constitute the complete power supply. If you can read them and understand them, you can actually create your own power supply, because the components that are required to create these are very cheap and very easily available in each and every town. The next topic that we will cater to is transistor. If you have liked the topic, please like, share and subscribe. Thank you.